my paper titled Make an Audio Text to Audio Generation with Prompt Enhanced Diffusion Models. So this was published in ICML 2023. So let's see how the paper is. Yeah. So before we dive deep into what the model is, I'll give an overview of how it works. So what you need to give is, you just need to type a prompt and it will generate the corresponding audio. So I tried few examples. So here are the samples. We have, when I typed a bird chirps, this was the audio generated. And then when you type a girl sings in rain, and then on typing thunderstorms, this is interesting, right? Now let's gradually see how it does what it does. Yeah, so first of all, let's see what's new in Make an Audio. Like, what was the research gap it tried to address? So this was not the first model which did this prompt to audio thing. So there had been several papers there. So we had great models in 2022, Audio LM and Audio Gen. So Audio Gen, it had some limitations. It was like regarding, it was not able to handle complex prompts. So in this Make an Audio, what will happen is, I showed you simpler prompts like bird chirps and all. But had I typed like thunderstorms before the rain, or something like 2-3 words composition together, even such prompts Make an Audio is able to handle. It's able to generate prompt. But that's not like happening with Audio Gen. It doesn't handle complex prompts. As well as, and there we already had Audio LM. So this Audio LM excels in structured content, but it's less flexible to like diverse data sets. So what it means is, Audio LM is more diverted to speech generation and music generation, but it can't handle any kind of sound or like diverse sound varieties. So all these things have been addressed in the Make an Audio paper. So and it also brought some new changes to the architecture. So these models were introduced in 2022. It came right after it in 2023, and then it also incorporated CLAP model. So all of you would have been aware of CLIP model, which is a pre-trained model which is like learns the attention between image and text. So that happens in CLIP. So that image part is replaced with audio, and they have made a CLAP paper. This came in ICASP 2023. So this the pre-trained models advantage has been utilized in this Make an Audio paper, because now that you are using representation, common representation space of audio as well as text. So that could have been an added advantage, so which has been utilized in this paper, along with pseudo prompt enhancement. So we see that like usually all such models, we see DAL-E and even all those OpenAI models, everywhere image generation, video generation, text to image and video, those things always had been coming first. Audio was always like a step behind. Why was it so? It was because there was a shortage of audio captioned data, huge data set of high quality. So that had been a constant drawback. So what these people did, say, there are popular speech data sets, like many data sets, which do not have captions. So what these people did, they have introduced this pseudo prompt enhancement technique, so that we can use uncaptioned data as well. Also CLAP embeddings they have used. And also one more advantage here was the latent diffusion model. So like all those models had been working on discrete raw waveforms. Okay, like it's like converting text to discrete tokens and like handling all discretized things. But these people through latent diffusion had tried addressing making a continuous waveforms and doing this on spectrograms. So this is the model architecture. So for training we will need captioned audio data, and then output will be the reconstructed audio. So this looks pretty complex, so I'll gradually take you through each of the components step by step. So before starting anything, like any of our data science related work, first what we need is the data set. The good the data set, so better the results. So these are the data sets these authors used for the make an audio paper. So here they have divided it into 3 components. If you can see, the first portion is all the data sets having captions with them. They got it with caption. The second set they had only labels, and third sets had nothing. Like it was language free. It didn't have any labels. So they want.
What do you mean by label and captions? I mean, how are they different?
So caption is, say they have a raining sound, and it is captioned like it is raining. But label data set is like it's usually for sounds. Like this is the thunder. Yeah, rain. That's how it is. Like it's just name the sound with one label, not a sentence or like not in continuous present tense. It's just the.
How they can differ to thunderous storm in a separate name or a single name?
Single label. Like thunders also. Thunder means the single name.
So if there is like 3 or 4 variety of thunder, how we can
No, this is predefined label, like data sets. So this Sony's game effects, V sound effects. So these are sounds. So it will have sounds like piano sound. So piano, this is the sound. Like that, they have the discrete labels with the sound.
discrete?
One label. Say this is tabla. So they like tabla sound is the audio of tabla playing. But if that is with caption, it will be like tabla playing. Like that, they will have captions. But here, like single word. You are asking something?
I'm saying that whose sound is this?
Yeah, that's all. What is it? No description. Elaborative description is caption is what is. And this last two ones are like language free. They have nothing. Someone speaking and that's recorded. So they wanted to utilize all this for their as the data set for them. So how do they do that? They use expert distillation for audio captioning. So they use two. First of all, they use two pre-trained models. Say for language free audio, they are providing captions. So there are already pre-trained models for assigning captions. So there are 2 papers like automatic audio captioning and audio text retrieval. So what automatic audio captioning does is, it given an audio, it will generate the natural language descriptions. It's trained in that. And then audio text retrieval, what it does is the reverse. You give text, it will give you the corresponding audio. It will have a database collection of audios. So given the text, it will pick the corresponding audio. So since they want the best captions, what they did, they used both of them. So with the first model, they'll get the audio's text like captions. Second model then uses that caption to generate to collect the audio. Then they'll match if it's the same and use a trade-off between them. And then using the joint knowledge distillation for both of them, they'll like come up with some text captions, and then and how to select if it's good. Like we can't hear everything and compare, right? So for that comparison, they are using a method called CLAP score. So CLAP is contrastive language audio pre-trained. So this CLAP model is pre-trained like text with audio. So audio captions, it's like you have audio and caption in their latent space. It brings it to a common space and finds attention between them, like scores between them. And that's how it has been already trained. So it has the knowledge of audio text pairings. So that will use its knowledge to score if this captioning is good enough or not. So they filter
So in CLAP, they are using caption or label?
They are using caption.
In clip model, they are using label.
Yes, sir. Oh, and no, clip also I thought it's caption.
Clip caption.
That's what Vinod sir taught us in class. Yeah, that's caption. Caption. Yeah, so they did an ablation kind of study for this expert distillation method also. Like original is the raw data set, and yeah, they used captioning as well as retrieval, and then also use the clap selection on them, like clap based selection. So obviously using captioning, retrieval as well as the clap score selection ended up giving them the highest clap score. So to confirm having the good captions. Then also they experimented with the various prompt types, like to make the prompts more conceptually relevant. What they did, they created these templates. So these like B stands for verb, and like A for adjective, N for noun. So such template they have created, and then it's like it's raining before the sun, like before the bird chirps. Then both of the sound will come concatenatedly. Like first raining will happen and then the bird chirps. So like that they have created templates to write prompts in a more elaborative way, so that it provides more conceptual relevance to the audio. So for now we have like input text and the audio. So we need to represent them in a like in encoded latent space. So first we represent textual text data. So for that they are using pre-trained encoders, BERT, T5 large. So these things and clip clap, all these things they tried. All these things have inbuilt transformers like for textual encoding. So they tried encoding using all these models, and then they see that clap and T5 large are showing like good performance, like they are giving good embedding scores. So why could it be? They have also provided some observations. So clip is not giving good representation because it's trained for image and language, right? Image text pairs, and we are dealing with audio. So obviously it's like we are convinced that it's not able to give good audio embeddings and audio related textual embeddings. And then clap and T5 large both show similar performances, but clap seem to have lower number of parameters while training, so compared to T5. So that helps in computational efficiency. And then for one more thing was for large language models, T5 large has nothing to do with audio. Look, see, it has, so for there what you need to do, it does textual embeddings that we need to explicitly store offline and then use it for training our diffusion models. But clap is like, it has text audio latent representations in common, so it knows the coordination between text and audio, so it helps in navigating the diffusion process easily. So that's why you can like on the fly perform embeddings as well as diffusion in a flow. So that's why they prefer clap model. Now that we have encoded our text, we have represented it. Now we need to represent our audio as well. So for audio representation, like first, what is spectrogram? So audios, we would have seen the audio waves, right? Amplitude we capture at waves, point intervals. Everyone would have studied in physics somewhere. So that thing we converted to a spectrogram. That's like appears as like image format, but what it does is like converting, like usual thing we have in amplitude time frame. We capture amplitude at various time intervals. That thing we are converting to frequency time domain. So and that representation is captured in spectrogram. And here usually they deal with MEL spectrogram as we can see. So that's nothing but having them in MEL scale. So that is more having more perceptual relevance. That like we humans how we infer. So it helps in converting it to log scale and helping in that relevance. So so now audios are all converted to spectrogram, and now we need to use the encodings for them. So our spectrogram encoder has three parts: an encoder network E, which takes samples X as input and outputs latent space representation Z. So for this, they are using variational autoencoder. So they are like taking any audio sample and taking Mel spectrogram and representing it in a latent space. Z. And then a decoder network G, which reconstructs the Mel spectrogram signals X from the compressed representations. So now reconstructed is represented as X prime because it's never exactly the same. So that's what we reduce, like X prime minus X, we need to reduce that loss function. And then multi-window discriminator is also there, which learns to distinguish the generated samples, G of Z, the one which came out reconstructed, if that is like how close it to the real one, like discriminating it as real or fake, that is done by this discriminator. So this whole system is like trained end-to-end to minimize the reconstruction loss, like we want the generated one to be close to the original ones, and the GAN loss, like the decoder of the variational encoder can be used as the generator in a GAN because we have got audios. So now that we have used an additional discriminator. So we'll see that the generator one discriminator will try to classify it as fake, and then it goes again in a loop to create as good as to fool the discriminators. So this cycle is like a two-player game to fool each other. And then also we have the scale penalty loss. So this is scale divergence loss, which tries to bring the encoders to learn the standard and avoid arbitrarily high variance latent spaces. So it makes sure that the audio audio representations which has been reconstructed is like close enough to the normal standard representations and not diverges a lot. So now that we have encoded the audio and text, and then we'll have to we have a generative latent diffusion model. So in this latent, so we must have heard about diffusion models, but this is latent diffusion model. So the difference is the usual diffusion models are like taking the raw audio forms and then adding noise stepwise in the noising forward process, and in backwards it tries learning the denoising, which is called denoising. There it tries to learn the noise and trains in that way. But in latent diffusion model, we are not dealing with raw audio forms, but we just saw that we use variational autoencoders to convert the spectrogram to a latent space. So from that space, it picks up the latent representations and does the diffusion process. So it helps in faster computations. Like latent representation means we have already reduced the dimension of the features to a lower space. So now it has easier way to learn it. And it's not just diffusion model, but it is conditioned on textual representations. So it is like conditional diffusion learning. So what it does is, given the text, we had that text embedding. So and we use clap transformer model, right? Clap model to have the representation of text audio pulled together. So this text helps in guiding the diffusion process. When it tries to learn the error and tries to recreate the original signal, this text will guide it to the correct audio, to reach it to the correct audio faster. But not just condition, but that way it might be that we have guiding that way of diffusion will ensure good fidelity. But the problem is there could be some overfitting, like we might not get diversity, only the original image may get recreated. So for that reason, they are also doing this classifier free guidance. So unconditional as well as conditional both have a trade-off. Like you are giving the conditions and at sometimes not, and both we are having a trade-off to get the flow of this diffusion training. So here's a question for the audience. So how can we use the same diffusion model of conditional classifier guidance for unconditional as well? So if we have prepared it for conditional classification, and I do not want to create something else for unconditional, but do minor changes here and use the same model. So any idea how to do that?
So, what is the diffusion model and
What is that?
can you please explain what is the diffusion model?
So in diffusion model, it's like there will be a see here we had our audio which got encoded in a latent space. So from there it will pick up an audio and an audio distribution you see, and then it will gradually stepwise add noise. Noise means some randomness, which is the Gaussian noise here. So from that distribution, it will take some elements and it will gradually add. So that is called forward process. In forward process, slowly it will add noise and change. Now, if you add noise to the original audio, it will change it, right? It will first make it flicker and completely the originality will be gone. It will become blurred, like completely gone. So it reaches that phase. Now it has to come back and get the original audio again. So for that, it will now go backwards and try to learn, okay, what was the error noise we added previously. That noise it will try to train on that noise. Like that will be the learning parameter. Like weights we had in here, like that it will learn the noise here, and then it will gradually move backwards, and like the entire process will go until it is able to create the original audio back. Yeah, so the answer to the question. Any attempts? Okay, so this is simple, just that you have that condition CT also in the formula. So what you need to do is just add CT equal to 0. You add an empty prompt in that place and then do the same thing. So when it's just an empty string there, but the model is the same and the process goes on. Yeah, so we have reached the results. So here reference means ground truth. So for that they have calculated clap score, and FID stands for fresher inception distance. So it measures the distribution similarity between generated and real audio features. So lower FID means we are having good audio, we created. And then KL divergence, it measures how much the probability distribution of generated audio diverges from the real audio. So lower the divergence, better the audio quality. And then clap score we just saw previously, right? It has the semantic alignment between audio as well as text. So that helps and it uses cosine similarity to get a score between like how much they are semantically aligned. If it's telling something, is the audio representing the same meaning? And then MOS here means mean opinion score. So this is qualitative analysis. MOS here means they have given it to people in real and they have rated it. This is the tab you can see on the side, right? Select this one. Select an option. So these were the options given to them, and they had to rate. Okay, after hearing, and Q is for quality, F is for like FID score. So they have to tell if it's good quality and also if the text and audio aligns well. That is coming in the MSF. So these things in these 5 categories, people have rated the audio, and this FID, Z, and TL we are getting from the model. Z here stands for zero shot. So after the entire training is over, they have used Clotho validation dataset and like that, which is new one for the model, and they have randomly given a prompt from there and checked if the audio is alignable. And Clotho has like 5 captions for every audio. So we have something to verify.
For every audio means for every sample.
Yeah, for every sample they have given 5 captions with the Clotho dataset. So that we have ground truth also, and this will help us compare and get the score. So here they see that using clap for text conditioning helps the best. It also has less number of parameters, low FID, low KL divergence, and then high MOS scores as expected. Yeah, and the limitations, the authors have themselves cited some limitations in their paper. So this was like diffusion. They are using this diffusion model, right? So they are claiming that it's taking more number of steps to generate real, more fidel and good quality audio. So that's being computationally more expensive. So this was the limitation they stated, and they have also come up with Make an Audio 2, where they are using some other diffusion models. So you can give it a read if you have time. Then they have tried addressing that issue as well. And also in this paper itself, I have covered all about text to audio, right? but they have claimed that this can be extended to like more user specific conditions, like also like multimodality. You can use the same model with minor changes to X to any like any modality, text to they claim generate audio from any modality, be it image or audio also. Say given an audio, you want to complete it using some in-painting, that also can be addressed. And also more like user-specific things, like given an image, you want some audio to it, or insert, like in image they had like insert some image in a scenery. Such things are happening. So likewise, they are trying to do with audio as well. So those are the possible extensions they have proposed in this paper. So yeah, and any more limitations which you feel you can see in this paper, please do suggest.
How they are handling the noise. And the other thing is that in the training time, are they using the same duration of the audio or?
Yeah, they have pre-processed it in a way that there is only 10 seconds of audio. So if the audio is smaller, they are like padding and turning it up, and for bigger audio, it will just get cut down. Yeah, they are maintaining it a constant so that the trading is smoother. Yeah, any limitations, please? That will help me in my research.
It's not a limitation.
Huh.
There is one paper, Salsa.
Okay.
IISER 2024. So they have mentioned that in audio gen models, what is the exact like limitation? Why they are not able to, as you said, that they are giving 5 parameters. So if we talk about the gradient will be like their alignment is very crucial. So we'll like leave that given up. We will get to know that why it is working, why in some ways it is not. Just a solution.
This gap model can handle the different duration audio size
Different duration of the
for the training. Like, as you said, that
yeah, I mean, they have done it for smoother trading. I don't think that is anywhere a limitation for handling different size audios. That shouldn't be a limitation. Just for a smoother processing is what I feel. That's what they justified it to be.
so they fix to the 10 second.
And clap is a separate model in like that is a separate paper which came in ICAS 2023 something. So that you may give a read if you are very interested. Thank you.
समोसे आए हैं अंदर लगभग
अरे बाहर ही ले लेंगे गंदा हो। खत्म ही
वो
हुआ।
आया नहीं तो निकल जाएगा
अरे खत्म हो गए ये
तो अब मैं सब करवा देता
5 मिनट।
How this will be extended to image to audio?
That I have not covered yet. That is out of context for today. But it's given in the paper. I can tell you tomorrow or after 1 hour.
You said that it can
Yeah.
be extended to any task.
Yeah, X2
So
model.
how you think it can be extended?
I mean,
कुछ
they-
फोटो पेपर में नहीं जानना है आपको कैसे? What will be the problem? What will be the limitation? What extra changes you have to make? Solution is what your thought process.
X2 audio means
Cross to hey image to audio.
image to audio. Now instead of text, there will be passing image. So it will be they will have an image encoder, and which like we are having spectrogram encoders differently, and text encoder separately as of now.
ठीक है extra image encoder लगाने से हो जाएगा.
And then we'll use clip instead of that. Clip will help in better the image. No, image audio, right? Yeah, image to maybe we can convert image to text and do the same. It's there in the paper. I'll give a link.
This will also work if the voices are overlapped. If two voices are overlapped, like you were saying, the rain sound and the word sound both are overlapping, then the quality of the audio is they have that kind of audios where multiple voices are like overlapping and still they are echoed.
They have claimed the longer prompt audios, like like it's raining and the thunderstorms. So they are like there is a sequence after rain, like before it's raining and after that the thunder is storming. So they have addressed this issue. So I think they do not have any overlaps maybe.